Hello, we're going to talk about Chapter 6 in Statistical Methods, STA 2023. The first section I'm going to go over in this video is not really in Chapter 6. It's kind of covered in Chapter 1, but I feel it's a good place to review it in Chapter 6 because we talk about how correlation does not imply causation. So how can we establish causation? And one way is through an experiment. So we're going to kind of review experiments here. So notice in principle, experiments can give good evidence for causation. So some definitions: experimental units are the individuals on which the experiment is done on. Could be also considered participants. Subjects, human being experimental units. Treatment is a specific experimental condition applied to the units. Factors are the explanatory variables. Placebo is the dummy treatment, and the design of the experiment is the choice of treatments and the manner in which the experimental units or subjects are assigned to the treatments. Note, control is the first basic principle of statistical design of experiments. And control group is the group that receives the sham treatment. Now, having said all that, let's kind of make this real a bit. So let's say you all come in and you have this really bad headache. And I said, well, I know that aspirin and beta-carotene could help. So we would call the aspirin a factor, the beta-carotene another factor, and if we're mixing them, we can make a table to show that we're mixed. So our factors are aspirin and beta-carotene. Now, notice that each factor has two levels. Yes, you get it. No, you don't. Beta-carotene, yes, you get it. No, you don't. Now, levels could be 3 pills, 2 pills, 1 pill, no pills, but if it's not given, then you assume, yes, you get it. No, you don't. So this table shows that we're going to have one group, yes, aspirin, yes, beta-carotene. One group, yes, aspirin, but no beta-carotene. And notice I put a placebo in there. The idea of having a placebo is that we'll have each group having 2 pills, even if one pill is a fake pill. Then this group will receive yes, beta-carotene, but no aspirin. I put a placebo in there. And this group will receive no beta-carotene, no aspirin. So for example, if I didn't give you anything, you may say that it's not really helping me. But if I give you 2 placebos, everyone's getting 2 pills. Now, just to review, we have 2 factors. Each factor has 2 levels. And notice for this experiment, we're going to need 1, 2, 3, 4 groups. That's because we have 4 treatments. Treatments are specifically what each group gets. So our 4 treatments are aspirin beta-carotene, aspirin placebo, placebo beta-carotene, and placebo placebo. So 2 factors. Each factor has 2 levels, and we need 4 groups because we have 4 treatments. And the table helps us figure out what they are. Now we can go into our design. When we do our design, our flow chart, notice it always begins with random assignment. The reason for that is we want to make sure we don't put all the males or females in separate groups, or all the really bad headaches in one group and the light headaches in another group. We want to mix up the people. So is it the treatment that's taking care of this, not some lurking variable or outside thing messing up our study? So step 1, random assignment. We've decided we need 4 groups because we have 4 treatments. And then at the end, we're going to compare results. Now, which one will be the best? I don't know. That's why we do the experiment. We don't want to go in with any sort of bias favoring a certain outcome. We don't know. We just have to run the test and see. So we always start with random assignment, and we end with compare results. And randomization uses chance to assign subjects to the treatments. And the hope is randomization and comparison together prevent bias, systematic favoritism in experiments. So we've gone through all the definitions, and again, we always start with randomization. We end with comparing at the end. We want to make sure we control the lurking variables, things that are outside the study, randomize, and replicate. We want everyone to receive it the same way. Statistically significant is an observed effect so large that it would rarely occur by chance. This is going to be really important in the future. So remember, statistically significant. Basically, right now, it's something's going on. Something's going on. We want to make sure it's completely randomized. Good experiments require careful attention to details. And we'd like our experiments to be double-blind. That means the person administering, let's say the pill in this case, and the person receiving, neither one knows what they're getting. We don't want to tip off, like, ooh, how are you feeling? You're getting the fake one, or you're getting the real one. The researchers know what's going on, but double-blind would be an example of the person giving and the person receiving, neither one know what's the placebo, what's the real one. And you want to make sure that you have lack of realism. Subject to those treatments or setting of an experiment may not realistically duplicate the conditions. For example, if I want to find out how children interact with each other, but I put them in Disney World, they'll be hyped up with stimuli versus in a library when I really want to put them in a classroom setting, something typical. So here's one example. When during the winter season, many people develop a cold. Do regularly taking aspirin and or vitamin C tablets help protect people against a common cold? We want to conduct an experiment where a person takes 2, 1, or 0 of each tablet to help protect them against a common cold. So notice we have 2 factors, aspirin and vitamin C. Each factor has 3 levels, 2, 1, 0, 2, 1, 0. Because we're mixing, we're going to make a table. Doesn't matter which factor goes where, but we have aspirin 210, vitamin C 210, and notice the rows and columns are defined by the levels. So in this case, we're going to have 1, 2, 3, 4, 5, 6, 7, 8, 9 groups, 9 treatments. This one is 2 vitamin C, 2 aspirin, 1 vitamin C, 2 aspirin, 0 vitamin C, 2 aspirin, so forth and so on, till you get all 9 groups. Then when we do the flow chart, always starts with randomly assign. We put our 9 treatments in the center, and then we compare results. Some questions I can ask would be factors. So in this case, the factors are vitamin C and aspirin. If I ask for treatments, you would list all 9 treatments. 2 aspirin, 1 vitamin C. 2 aspirin, 1 vitamin C. 2 aspirin, 0 vitamin C. 1 aspirin, 2 vitamin C. 1 aspirin, 1 vitamin C. 1 aspirin, 0 vitamin C, 0 aspirin, 2 vitamin C, 0 aspirin, 1 vitamin C, 0 aspirin, 0 vitamin C. The response variable would be, well, how can we measure this? And we can measure this by looking at the level of cold, maybe white blood cells, maybe ask them how they're feeling. But we're going to, response variable is how we measure. The number of groups need to be 9. Do we have a control group? Well, we need a control group to be an experiment. So the control group would be 0 vitamin C, 0 aspirin. And then possible lurking variables would be things that can mess up our study. For example, allergies, or the environment, or other conditions, or diet, or severity of cold. There's things that we have to really consider when we're looking at this. Okay? I'm going to go over 3 more experiments for you, just to make sure we have the idea. So here's a Valentine's experiment. So we're going to try online dating to see if we can find a date. And that's all the information I've given you. So since we only have 1 factor using online dating, I'm not going to make a table. We're not mixing 2 factors or more. So since we only have 1 factor, we're not going to make a table. So our flow chart would be randomly assign. We're going to have 2 groups. 1 group does online and 1 group does not do online. Remember, we need a control group to be an experiment. And at the end, we're going to compare results. So to answer those questions, this time we have 1 factor online. We have 2 groups because we have 2 treatments. 1 group gets online, 1 group not online. The response variable could be number of dates. We could count that. A control would be the group that doesn't try online. And then some lurking variables, your personality, if you don't have internet, if your internet's sketchy and not effective. Somebody put catfish, so if you're not representing yourself online. Okay, next one. Let's say, again, we're still sticking with the theme of Valentine's Day. You want to have a good date. You got your first date, and 2 things you can do is have flowers and or planning to have a special first date. So in this case, we have 2 factors and we're mixing, but I didn't tell you how many flowers or how much to plan. So for our table, we have flowers, yes, no. Planning, yes, no. So we end up getting 4 groups. Yes planning, yes flowers. No planning, yes flowers. Yes planning, no flowers. No flowers, no planning. We don't know which is going to work best. We don't want to have a bias. So then we know we have 4 groups. We can do our flow chart. Randomly assign. 1 group gets flowers and planning. 1 group gets just flowers. 1 group gets planning. And 1 group gets no flowers, no planning. Notice we didn't put a placebo because not always a placebo makes sense in this case. In this case, it doesn't. And then at the end, we compare results. So here, our factors are flowers and planning. We have 4 groups, 4 treatments, flowers and planning, flowers only, planning only, no flowers, no planning. We do have the response variable could be getting a second date or give the data survey, probably not the most romantic. And then a control group would be no flowers, no planting. And then some lurking variables, you could be allergic to the flowers, if you chose a bad restaurant, etc. Now the last one, we have two factors. So let's say it's a 1-year anniversary and you want to make it special. The two factors now are jewelry and or vacation. So for jewelry, we have levels this time. 2 pieces of jewelry, 1 or 0. Vacation, 1 you go on it, 0 you don't. And again, we want to have a special 1-year anniversary. So our table would be vacation, level 1, 0. Yes, we go. 0, no, we don't. Jewelry, 2, 1, 0. And this will show our 6 groups that we need, our 6 treatments. So one group will be yes, go on vacation, get 2 pieces of jewelry. Another group would be yes, we go on vacation, 1 piece of jewelry. Another group, no, yes, we go on vacation, but no jewelry. Fourth group would be 2 pieces of jewelry, but no vacation. Fifth group would be 1 piece of jewelry and no vacation. And the last group, no jewelry, no vacation. And you're probably saying, we want to go on vacation and 2 pieces of jewelry. But again, we don't want to assume. We just run the test. We don't have any bias. Who knows which will work best? Then our flowchart we randomly assign. We put our 6 treatments in the center. At the end, we compare results. And remember, our factors are having jewelry and vacation. Treatments, we list our 6 treatments. The response variable could be the level of relationship. Some people in class would say, if you get married, depending on how you want to measure that. Number of groups needed 6. The control group would be 0 jewelry, 0 vacation. And then lurking variables, if you have a bad vacation, if someone gets sick, if the jewelry is fake, all of those ideas. And again, this was Chapter 6, Supplement section.